Bridges are an essential part of civil infrastructure around the world, being a part of many major railway and road networks. They provide us with the ability to travel over rivers, valleys, and other obstacles using a much more direct path than alternatives. The objective of this project is to create the lightest bridge possible entirely out of pasta that can support the greatest load. The rules for the bridge were that it must span a minimum distance of 350 millimeters with a maximum width of 80 millimeters. It was also required to weigh in at less than 200 grams net weight and be constructed entirely out of superglue and pasta. The bridge that we chose to design was a simple truss bridge with two main supporting beams that run along the edges of the deck the whole way along the bridge. It also had a truss assembly on either side running the full length of the bridge with two connecting beams across the top of the two trusses and connecting beams spanning the width of the bridge along the deck. The truss structure was used as it helps to spread the weight more uniformly across the span of the bridge instead of concentrating it over one point. The use of multiple cross-bracing beams was good for adding support and stability throughout the length of the bridge. The bridge, taking up the full 80 millimeters worth of width, also allowed us to provide the bridge with a strong stability.
In the photographs that are shown above, this is showing the construction of the spaghetti bridge that was created using hot glue and dry pasta. Through measuring, cutting, and assembling the pasta into groups of 3 strands, this was the most beneficial way we have to make a strong but also lightweight bridge. The use of triangular bracing was incorporated into our design as it was proven that triangles provide strength and stability throughout the bridge. Hot glue was used to connect each pasta at a joint to ensure the structure was rigid through the assembly. Creating accurate dimensions when constructing the bridge was important to ensure that the loads could easily be transferred through the bridge. Planning and precision and a basic understanding of truss systems was the best way to create a strong but also lightweight bridge. Once the design was completed, the design was ready for testing by adding simple weights in which the bridge could withstand before snapping. Through building the bridge, it was observed that the bridge needed to be longer to be able to stand on the apparatus in which this will be discussed below. Once the design was built, it was then time for testing. Through this bridge, it was put onto a mechanism in which the weight could be added to the design to test the durability of the bridge. It was soon discovered that the bridge needed to be longer to hold onto the supports while weight was added. The bridge never snapped due to the slipping of the supports. In this, before the bridge slipped, the weight got to 1 kilo. Through further discussion, it was apparent to us that the bridge needed to be built another 5 centimeters longer to ensure that it could withstand the weight of the apparatus. A positive to the design was it was lightweight, weighing in at 35 grams, which meant the bridge was very underweight, which is something the group aimed for. Adding more weight to the bridge could have meant that the bridge would have held more weight. For future reference, creating a longer bridge that had more support would have further benefited the design.
The bridge was constructed entirely out of spaghetti and fixed together using hot glue. When using spaghetti as the only building material of the bridge, careful planning is needed to ensure the bridge is able to function under heavy loads. Hot glue was used as the primary fixing material, which, unlike other alternatives like super glue, which takes time to set, hot glue dries in seconds, similarly to how a bridge is welded. Although hot glue has its advantages, it had added some additional weight to the bridge, so some parts of the bridge could not be added, like supporting members across the top of the bridge to evenly spread out the forces over the bridge. Without access to a kitchen scale, bridge building had to be stopped prematurely as a maximum of 200 grams could not be exceeded. Once testing had started, it was found out that the bridge was 35 grams, well short of a 200 gram maximum. With the bridge being so light, it lacked structural integrity, which was found out during the testing when the bridge only held 1 kilogram. Because it was missing key components like supporting members and joists, which would have significantly increased its load-bearing capability, shown in figures 4 and 5 below. The comparison between bridges 1 and 2 has shown that bridge 2 is stronger, more effective design. Data collected from bridge simulation has shown that the bridge 1 failed under 72 kilonewtons, and Bridge 2 supported 100 kilonewtons before failing. The increase of 28 kilonewtons showed a 39% increase in strength. These results concluded that the second bridge design has a higher load-bearing capacity. The reason for a major improvement in the second bridge is a supporting top joist, which has an increase in structural strength of the bridge, with forces distributed evenly throughout the middle of the bridge. In Bridge 1, since there is no supporting joist, when the load is placed in the middle of the bridge collapses in on itself, resulting in a failed bridge. The top supporting joist in Bridge 2 spreads out the load of the bridge so that it can experience higher loads before reaching complete failure, reducing the stress on individual strands of spaghetti, acting like steel in a bridge. The bridge simulation shows that the truss configuration in Bridge 2 was more efficient at sharing loads than Bridge 1. The bridge incorporates a triangular design that has been used in many bridge designs around the world, like the Sydney Harbour Bridge, which has triangles incorporated into the arch of the bridge. The addition improved the transfer of forces under load. The bridge maintained structural integrity under load when heavier forces were applied. An important factor is the reduction in weak points in the bridge. Bridge 2. Bridge 1 had fewer reinforced members, meaning that some joints carried more stress, resulting in poor performance. This created crucial stress points in the bridge, leading to its collapse at 72 kilonewtons. Bridge 2 minimized this issue by adding an additional load paths which distributed the forces evenly throughout the structure. This allowed Bridge 2 to withstand an additional 28 kilonewtons before failure. The data of the simulation has shown that Bridge 2 is stronger and more reliable. Although both bridges were constructed out of the same material, it had similar dimensions. The additional member in bridges has had an increase in the overall bridge performance. Overall, evidence leads towards supporting that Bridge 2 was a stronger, more efficient design since it proved its greater strength. Since it had greater strength, improved stability, and more efficient force distribution. In conclusion, it was established that Bridge 2 performed better than Bridge 1. Both bridges were made out of similar materials, almost equal in size, but the capacity to hold loads of up to 100 kilonewtons in Bridge 2 significantly increased compared to 72 kilonewtons in Bridge 1. The effect, there was a 39% increase in performance of the Bridge 2 designs. The ability to hold loads of up to 100 kilonewtons is mainly due to the reinforcement in the top chords and designs of trusses in such a way loads are evenly distributed throughout the bridge. Triangular bracing was incorporated into both bridges, making them rigid. Consistently, stress was minimized through the elimination of any weak points in the bridges. All of these led to Bridge 2 to endure more tension and compression forces to Bridge 1. In summary, it is quite clear that the design and building of bridges are key elements in engineering. This is because the slight variations of designs result in an improved efficiency.